Welcome to Mechanical Tutorials. I'm going to teach you different techniques in SolidWorks for mechanical engineers. So before starting FEA analysis, we should understand basics about material properties and material types. So how do we select material? There are n number of materials in the market like steel, plastics, wood, cork, glass, ceramic, rubber, copper. How do we select different materials for different components? So for that we have to understand about some of the material properties, and this is about stress strain curve. So the linear slope is where the material doesn't deform at all. So there is a uniform thickness on the material cross section. So when it reaches tensile yield strength or simply yield strength, it start deforming. So yield strength is nothing but maximum stress where a material start deforming permanently. That is called plastic deformation, and it is measured in Newton per meter square or pascals, or we can use PSI also. Next is ultimate tensile strength or simply ultimate strength or tensile strength. It is called UTS, where the necking of the component takes place. So tensile strength is maximum stress at which material start failing or breaking. So there is a slowly breaking of this component and finally it fractures. So usually we will consider where there is no plastic deformation. So the stress at which where there is no plastic deformation, that is tensile strength or tensile yield strength. So in material properties, when we apply material to any component, we have to consider at least 4 factors, that is elastic modulus. This elastic modulus is sometimes called Young's modulus, that is the slope of this stress strain curve. So this gives the rigidity or stretching or bending of the component. So how rigid is the component, it defines. Next, Poisson ratio I am going to explain in the next slide. Mass density. The density will gives us the idea about approximate weight of the component. So for same strength we can have different density, and that results in weight of the component. Sometimes weight of the component is very much important while designing aircrafts or automobiles. So this is very much important. Next property is yield strength. I have already explained. So the yield strength is maximum strength at which the material start deforming. So these 4 are important. So in Poisson ratio have the range of 0 to 0.5. So cork is having 0, glass is having 0.05 to 0.01, rubber is having 0.045 to 0.5. So rubber is having the maximum value 0.5. So if any value is near to 0 is brittle in nature, and any value which is near to 0.5 is elastic in nature. So it works like a rubber. So based on that, based on our application, we can select the material. So Poisson ratio is very much important while selecting the material. Sometimes we design very good product with good material, but suddenly it fractures because of brittleness. So Poisson ratio is very less for this component. So we have to be very much careful. So steel is having 0.27 to 0.3, aluminum is having 0.33, cast iron is 0.2 to 0.3. See, cast iron is very much near to glass, so it is brittle in nature. Some common metals is having 0.25 to 0.4, brass is having 0.33, copper is having 0.285. So let's see these different materials. Steel is having 0.27 to 0.3. Plastics are having 0.3 to 0.36. 0.16 is having wood, and cork is having 0. Glass is having 0.05 to 0.1. Ceramic is 0.25. See, 0.25 is very much near to 0. So it is brittle in nature. Cork also is brittle in nature. Rubber is having 0.5. It is elastic in nature. And plastics and steel are lying between brittle material and elastic material. Now copper is having 0.285. So Poisson ratio plays a major role while selecting a material. So when we understand different components while doing the analysis, we'll get more idea on these material properties and selection of material. So let's go to the example. Here I am going to show you finite element analysis of cantilever hook. So it is mounted on the wall. I am going to show you how it's going to develop stresses when load is applied at this end. So this is the hook. It's mounted on the wall and it is fitted with bolts. Now we are going to analyze how we are going to apply the boundary conditions. That's very much important. So these 4 holes are fixed with the bolt. So I'm going to take these 4 as fixed locations, and here I'm going to apply load. Sometimes we can split the surface and select this any surface for applying the load, but at this moment I am taking at this location. So let's start now. So this is the simple cantilever hook. These are my fixed conditions, and here I am going to apply the load. See, these are the dimensions. I am going to upload this PDF, so you can download this PDF for further reference. I am going to write the link in the description. So let's start the simulation study. Here I am going to focus on deformation and stresses. So create static study. Here the material it has taken automatically, it's alloy steel, otherwise we can change here from this location. Right click and click materials as we do in part modeling. Next I'm going to apply fixture where these bolts are going to hold. Since it is a single component, we can directly use fixture, otherwise we can use connector in the assembly. So okay. Next I am going to apply the loads. So add load. Here I am going to apply 100 newtons. So I am selecting this edge. See, direction is very much important. So here we have to select the plane. So 100 newtons. Now I have to go for mesh. So create a mesh. Say OK. Keep it as default. Don't try to reduce the mesh size, otherwise it takes a lot of time. So I am running the results. So we can see the results now. Let's analyze. So after generating report, we can see the maximum stresses developed on this component. So these are the fixed faces, and here maximum stresses are developed at this corner and this end point. So since there is a deflection at this location, stresses are not much considered. So we have to consider the stress at this location. So how do we reduce the stresses? Sometimes we use gussets or sometimes we use fillets to reduce the stress. So maximum stresses are developed at this location. So von Mercier stresses is 69 megapascals. And we can see the deflection. I am keeping in front view. See, this is the deflection because of this load. So maximum displacement we can see at this location, and it is around 0.303. So how do we conclude the results? So this is the material properties. Here we have to consider yield strength, that is 62 megapascals. I'm sorry, 620 megapascals, and material is alloy steel. As we know, deformation is 0.03 mm, and stresses, internal stresses developed, that is von Mercier stress is 69 megapascal. So 620 by 69, it is around 8.9. So usually, so the 8.9 is factor of safety. In shortcut we say FOS. So usually factor of safety should be at least 2. There is no units for this, and based on our design consideration we can increase the value of factor of safety. So here the product is safe. So that's how we analyze any component while doing FEA analysis. Thank you.